The next spotlight is multi-step greedy policies in online and approximate RL, presented by Jonathan Efroni.
Hey everybody. I'll talk today about our work on multiple-step greedy policies in online and approximate reinforcement learning. The motivation for this work is basically the fact that multiple-step look-at policies in reinforcement learning give state-of-the-art performance, as everybody probably know. And for example, by combining MPC or by using MCDS in reinforcement learning, impressive empirical success has been achieved in the past. Although this impressive empirical success, theory on how to combine multiple-step look-at policies in reinforcement learning is scarce. In previous works, multiple-step greedy policies were combined in the improvement stage of policy iteration, whereas here we will deal with how to combine these type of policies in online and approximate reinforcement learning. So before I'll discuss about the contributions of this work, let me briefly discuss about what do I mean by multiple-step greedy policies. And we start with the natural age greedy policy. It is basically the optimal first action in an age horizon gamma discounted MDP, with the following total reward, as you can see here. In order to better imagine it, let's think about some tree search problem, such that in each stage we get a gamma discounted reward, and at the leaf we get the value function times gamma to the age. In this tree search problem, we have some optimal trajectory, some optimal path that achieves the maximal reward. And the age greedy policy is simply the first optimal action at the root. Here it's simply left. The kappa greedy policy with respect to VPy is defined by being optimal with respect to all the possible tree depths that we saw earlier, such that they are weighted with some kappa averaging. So it can be understood as being optimal with respect to this painting here. In order to use both the age and kappa greedy policy in online and approximate RL, which we want to do here, and we need to generalize a basic fact about one-step greedy policies and soft updates. Specifically, that soft update using a one-step greedy policy always improves the current policy. And a bit more formally, for any policy pi, consider the one-step greedy policy pi G1, and we have the following basic result, that the mixture policy of pi and pi G1 is always better than pi for any value of alpha. And this fact is used in a lot of works in online and approximate RL. However, and unfortunately, it does not hold for multiple-step greedy policy, and it holds only if alpha is sufficiently large. And a bit more formally again, consider the age and kappa greedy policy that we saw earlier. The mixture policy with the age greedy policy, with age bigger than 1, is always better if and only if alpha equals to 1. And for the kappa greedy policy, it is better if and only if alpha is bigger than kappa. In light of this negative result, we still wanted to try to give some natural algorithms, some natural solutions to this problem, meaning we wanted to formulate multiple-step greedy policies while still having theoretical guarantees. So in fact, we gave here some 2 timescale online multiple-step policy iteration algorithm that is doing that, and we analyzed approximate multiple-step policy iteration methods as well. However, we do believe that it is an open and relevant problem to explore what other variations we can do in light of the negative results that we saw earlier. So to summarize, there is an important difference between multiple-step and one-step greedy policies. And also, multiple-step policy iteration in the approximate case has some theoretical benefits as well that I did not discuss in this talk here, and you're welcome to the poster to further discussion. Thank you.
That's a cute meme.